So we're starting this new topic. It's in the chemistry book. It's chapter C3, and it starts off with some things that will be familiar to you. Okay, so we're talking about using the theory, the particle theory, or sometimes we might call it the kinetic theory. And it's all about explaining how materials behave by imagining that we can see the particles that they're made out of. So in year 7, you probably think, right, we can classify things as solids and liquids and gases, and we can explain the behavior of these states of matter by talking about how we imagine their particles are arranged. And there's two things we need to think about. What are the forces like between the particles? How strong are the forces between the particles? And what is the particles' movement like? And what is the spacing between the particles like? All right, so we classify things as solid, liquid and gas, and excuse me, we imagine we can see the particles, and we imagine that the particles are like marbles, like little solid spheres of stuff. Okay, and think what we learn lower down the school, we think particles, their particles are all touching. They're in nice, regular, straight lines packed together. Okay, and they can't change position, they're fixed in position. So in a solid, the particles are not staying still, but are fixed in position in a regular arrangement and all touching. Okay, they are vibrating, so the particles in the solid are vibrating. They have some energy, and the forces between them are holding them in this regular arrangement. The forces between them are strong. The particles are vibrating around a fixed point. Think what you can't do to a solid. Okay, you can't compress a solid. You can't squash it into a smaller volume. It's in a fixed shape, and its volume is fixed as well. Okay, so although we can change the shape, we can't make it take up less space. Okay, liquids, in comparison, have still got particles that are all touching each other, but in this case, the particles have got more energy, and they can move around each other. They can swap positions. Okay, so because of that, that explains why we can pour liquids. The particles can rub over each other and swap places. They don't have a fixed shape. They take the shape of their container, but they do have a fixed volume because they can't be compressed. They can't be compressed because the particles are all touching each other. When you have to draw the particles in liquid, it's quite hard to show them touching, but not in a regular arrangement like in this solid here. Okay, and then finally gases. We know that gas particles in a gas, we imagine, have big gaps, big spaces between them. And that explains why you can compress a gas. So gas is the only state that you can squash into a smaller volume, because of these big spaces in between the particles. Imagine we could squash this gas and the particles would get closer and closer and closer together. Okay, the particles have got lots of energy. They're all moving fast, and importantly, they're moving randomly. Okay, gases don't have a fixed volume. They're going to spread out and fill any container they're in. When we say fill, we mean they're bouncing randomly within the confines of whatever that container is. So if you made this box that this gas was in larger, the particles would just spread out more and still be bouncing around, yeah, in the whole of the space. Okay, so we've got our understanding about how particles are arranged in solids compared to liquids, compared to gases. We should be happy with the fact that the states can change from solid to liquid to gas, and we've got these words here to describe those changes. So if we put energy in and give the particles more energy, particles in a solid can get sufficient energy to become a liquid. They're melting. Liquid particles can get sufficient energy to spread out and become a gas. They're evaporating. Change colour. If we cool things down, take energy away, gas particles can lose energy and become closer together. Yeah, and a gas can change into a liquid. It can condense. And a liquid can change to a solid, like putting water into the freezer, turns into solid ice. Liquids can freeze. So I've done red arrows because we're putting energy in to go in this direction, and my blue arrows getting colder, taking energy away to go in this direction. When we say hot and cold, it's relative. Okay, it's relative, isn't it? So the solid to liquid state change could be at any temperature. It might actually be quite hot. So think solid changing to a liquid. Yeah, if you melt some gold, you've got to make it really quite hot, and then the gold, liquid gold, would change back into solid gold. It would still be quite a high temperature where that happens. Okay, but we refer to these points as melting point. Up here, here's our keyword, melting point, and boiling point. So both freezing and melting happen at the melting point, which we can measure in degrees Celsius. And evaporating, yeah, is a little bit different, but we could label this state change here boiling. I'll use a B for boiling. Okay, because evaporating happens at all temperatures, but is fastest at boiling point. And gases condense at their boiling point, which we can measure again in degrees C. Okay, so if we took water as an example, we used water as our example, then I need a different colour. Let's have this kind of purpley colour here. Our solid water, ice, could change into liquid water, and liquid water can change into steam. So water can exist in 3 states of matter: solids, liquids, gas. We know that ice melts and water freezes at 0 degrees C, and water boils and steam condenses at 100 degrees C. So it's important to remember that freezing and melting, we could change the word melting point to freezing point. We could change the word boiling point to condensing point. Okay? And those temperatures are fixed. Now this last word is used when there's a strange thing that happens to some materials, for example carbon dioxide. Okay, solid carbon dioxide, when you heat it up, can change directly into a gas. Okay, it never exists as a liquid form. Okay, so in normal conditions carbon dioxide will never be a liquid. Okay, solid carbon dioxide changes straight into a gas, and we call that state change sublimation. Okay, so if you've got a big lump of solid CO2, which you could, and we'd call it dry ice, it would change from that lump, solid, very, very cold, it would change straight into a gas. It's used to make sort of fake smoke in the theatre and in nightclubs and things. Okay, now if we think about temperature changes during these changes of state, this is my diagram here to show what would happen to the temperature. Look, as I heat up a solid. So I've started here with my solid with its regular arrangement of particles. I'm heating it up. Time is going on, and the solid is getting hotter, 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 hotter. When it reaches the temperature, which is its melting or freezing point, then rather than getting hotter, look, it stays at the same temperature. And that's because in this part of the graph here, the heating is increasing the kinetic energy of these particles, and they're vibrating more, they're vibrating more, they're vibrating more, they're vibrating more. And when they get to this temperature, they're hot enough to separate and start to move around each other. Okay, so at this point here, where the solid becomes a liquid, instead of the energy making the stuff get hotter, the energy is making the stuff, the particles in the stuff, move apart from each other. Okay, we could say that here the temperature is going up and the kinetic energy of the particles is increasing. They're moving around more. And then as you reach the melting point, the temperature doesn't go up, but the energy is going up because the potential energy of the particles is getting bigger. And that's because they're moving apart from their neighbors. They're separating from each other. Okay? Now, once it's completely melted at this point here, okay, all of the particles can now start to get hotter again if you keep heating it. So if we go back to water as example, here it's all completely ice, and here it's all completely liquid water. But here would be the point where your ice cube is melting and there's a bit of solid ice and a bit of liquid water, but the ice cube hasn't completely melted, and then the temperature would stay at 0 degrees C if we were talking about water. Okay? We'd call this the specific latent heat. We're going to come back to that idea in physics later on. Okay? So latent heat means the energy isn't making it get hotter, but it is giving the particles more energy by getting them to separate from each other. The arrangement of the particles is going to have more energy when they're a liquid. Okay? And so we can talk about, in science, the internal energy of a substance. And the internal energy is made up of how much kinetic energy have the particles got, because they're moving, and then also how much potential energy have they got because of their position. All right, so we've got two things that make up the energy in particles. This part is about temperature. Okay, so that's a bit of a harder idea, that when something changes state, that's the thing to take away from this. When there is a change of state, so melting or freezing or condensing or boiling, there's no change in temperature, but there is a change in the energy of the particles. Okay, that is quite a weird idea to get your head round. Right, that's what this flat part of the graph here shows. That is the melting bit. That is the change of state. Okay, and it takes a certain amount of energy to make something melt or to boil. Yeah, and that energy is about rearranging the particles into their state of matter. Okay, last bit. If you are aiming for grade 6 or higher, then you ought to be able to say, hang on a minute, I know some stuff about atoms. Okay, and we could talk about how our model, how our model doesn't quite work all the time. It has limitations. Okay, but it's a good model because it's simple and it lets us explain how things happen. So we're using these ideas to explain things that we observe, even though we can't see particles. Okay, we assume, in our model, we assume that the particles are solid spheres. Okay, so this is useful when comparing the properties, which we've seen, and we use the model in year 7 to talk about solids, liquids and gases. But particles can be more than just atoms. They could be atoms, they could be molecules, they could be these things called ions. Okay, they vary in size, and some molecules are very, very long and big and chain-like, like we saw in our digestion topic with starch and proteins. Okay, in real life we shouldn't think of them as spherical. Okay, they've got different shapes, and we've learnt in C1 that actually atoms themselves are mostly made of empty space, so they're not solid at all. So there's some limitations to using our model of kinetic theory, but most of the time it's good enough to explain the things that we're seeing. So in science we keep it. It's a useful model most of the time. That's what a model means. Okay, now your task is to answer the questions on the double page in your chemistry book. All right, so these are the questions here. I will put a printout of my notes in today's post, and the video will be. Sorry,